Thank you very much for this wonderful opportunity. Uh, so what I will cover, as since it's the RISC-V day, and we are all very excited to be part of this RISC-V community, I will take this opportunity to talk about India's RISC-V journey through the project named Shakti. I belong to the Indian Institute of Technology, Madras, a premier institution of India. I am a professor of computer science and engineering. We belong to the RISC group, which is Reconfigurable Intelligent Systems Engineering group of our department, which is entrusted with the project named Shakti. And I will describe the project Shakti, which actually defines the India's RISC-V journey. So this particular program, which we call as the Indigenous Microprocessor Development Program, was actually funded by the Ministry of Electronics and Information Technology of the Government of India. The microprocessor program, when it was funded, we were looking at three important facets. Number one, the instruction set architecture, which defines the interface between the operating system, the compiler, and the applications to the microarchitecture. That should be open source. And we were also envisaging a family of microprocessors, starting from the embedded devices to mobile phones, laptops, desktops, workstation devices, to high performance servers. And we were also looking at software, which is the most important component of any microprocessor development program, because that defines its usage. We were looking at software that is developed and supported globally. So these are the different classes of processors that has come out from the Shakti family. The first one that you see on the left side top corner is the E-class processor, which is an embedded class processor, which has a 32-64-bit RISC-V. It is an embedded 3-stage pipeline, and we are looking at something like sub 200 megahertz and useful for IoT and end devices. The E-class today supports several types of peripherals, including QuadSPI, UART, I2C, PWMs, and we have booted several varieties of real-time operating systems. We have developed this, and we have made the FPGA prototype of it. We have taped out this in the 180 nanometer of a fab in India, in a place called Chandigarh, which is in North India. We have a fabrication unit at 180 nanometer. We have successfully made the silicon for this. And the market equivalence of this would be the ARM Cortex-M series. The next which is on what you see on the middle, is the C-class, which is basically the controller class. This again, we have the 32 and 64-bit version, and it is a 5/6 stage pipeline. Basically, these can be used on industrial controllers, point of sale terminals, storage controllers, medium scale and low end routers and network switches. And we have also a series of peripherals that are qualified on this: the I2C, the UART, DMA, memory management unit, QuadSPI, SDRAM. We have basically booted Linux on it, and we have also booted certain security related layers onto this. We have made 2 chips of this. The full details of these chips I will tell as we progress. And the market equivalence of this controller class would be somewhere in between ARM A35, A55, Intel Atom, etc. The last class of processor that you see on the top is the I-class processor, which is a 64-bit RISC-V based, today 12/16 stage pipeline. We have gone from a dual issue to a quad issue now, dual/quad issue, and it's an out of order execution. This is one that can go on to mobiles, desktops, workstation, and a collection of this can go on to the servers and high performance system. Now, the market equivalence of this high class would be ARM A9, A15, A75, A77. These three are the three classes of processors, and these are now made open source. Anybody can download this processor. The RTL we have developed using a language called BlueSpec. BlueSpec is a language that has originated from the Massachusetts Institute of Technology, US, and it's one of the very, very highly productive languages. When we have written this whole thing in BlueSpec, and the code for all is available in our website. So there are many startups who have actually taken this up and started building systems around that. What is unique about this entire process, or what you see on the rectangles at the bottom, we are bringing in fine-grained fault tolerance, and essentially we can have lockstep based executions. We could have guaranteed interrupts, etc., that are extremely important for fault tolerant fail-safe systems. And those type of features we can superimpose onto any of these cores, essentially making them fault tolerant. We are also looking at AI accelerators, because today many edge-based devices need to be intelligent. They want to execute certain neural network based algorithms. So edge AI is becoming quite prominent, and we are looking at AI accelerators, and we have developed, and it is under test. And another very important thing is the security. As you know, security is something, it's like a habit, right? You need to inculcate at a very early stage of your, if a habit is something, if inculcated at a very early stage of your life, it sticks around. It's very difficult to bring in a new habit at an old stage, at your old age. Similarly, the RISC-V being a very nascent baby instruction set architecture, it gives us the flexibility to add more and more secure features, right? And that is something that that is quite unique about this entire effort. So in overall, we now have three classes of processors that we believe can be used to build several SoCs that can span across from embedded systems to laptops, desktops, to large scale large scale servers. And each of these systems can basically have fault tolerant AI intelligence and security superimposed on that, and to bring up a complete ecosystem. Now let me just talk about the chips that we have already made. We had made 3 chips from the IIT Madras, and all the 3 were first time silicon success. And I would like to present some of these details here. The first chip that came out was in the year 2018. This was done. We had full cooperation from Intel. The whole chip was taped out at Intel Oregon fabs using 22 nanometer low power. And we also had our local industry, Hindustan Computers Limited, HCL, who partnered with us to make this particular chip. The SoC configuration was it had a 2 UART I2C quad SPI. It had DMA. It had a tightly coupled memory of 128 KB. It had a SDRAM controller. It had JTAG based debugger. The operating voltage was 0.7 volt, and the operating frequency was 300 megahertz. It was the IO dominated design. We got maximum things out so that we could verify, see a lot of things about the core. Around 320 IOs, and the area was approximately 100,000 gates for core and 200,000 gates for the entire SoC. So this we named as RISC-V, the first chip that came out. It was successful. We booted the Linux, and the next chip that we made in India, this was in the semiconductor laboratory at Chandigarh using 180 nanometer. We call it the REMO. The same design that we did in 180 nanometer, in 22 nanometer, the same thing we repeated at 180 nanometer. And we had this 4 kilobyte cache instead of 16 kilobyte. That was the only change. And we had a lot more of tightly coupled memory. And this basically was a chip done. And these two actually validated the C class core across multiple technology nodes. One that was advanced at that time was 22 nanometer to oldest technology, which was the 180 nanometer. In the year 2020, we made another chip which is called the Ordronix. It is with a die size of around 5387 cross 5227 micrometer. It had a gate count of around 646,000 gates, and we had a frequency of 100 megahertz and 256 pin. This was again taped out at our semiconductor laboratory, Chandigarh, in a 4 metal process technology. And this was having multiple features. It had PWMs, SPI, GPIO, UART, Quad SPI, I2C, SDRAM, JTAG, and of course a frequency of 100 megahertz. This chip was mounted on a board which was actually Arduino compatible. So all the Arduino type of projects could very well be fitted onto this, and it can work. We also maintain the header size and other dimensions of typical Arduino boards, so that any Arduino based project can be ported very quickly along with the add-on boards onto this system. And this is this we call it as MOSIC, and this is the E-class processor. Very shortly, we will be taping out the I-class processor, and probably the next RISC-V day, I can make a presentation about the I-class. In addition, we have been working very closely with the industry. One of the other important achievement was that we have worked with Thales, and which on a project called SafeRV, which is basically supporting the fault tolerance. So Shakti SafeRV quad core was booted on the FPGA, and this is another effort in the multi-core framework. All the architecture that at the remaining 10 minutes I will spend on the Shakti software efforts. All the architectures that we had built are basically gets its fruit when we have enough software that can exploit the benefits of that architecture. So we had now worked very seriously. There's been a very big team that had been working on this. So we have booted a lot of bare metal software, right? And we have our own indigenous homegrown IPs, which are validated now. These are low-speed peripherals, and we have developed the drivers for them at the bare metal level. Today, an embedded C program can be done quite successfully and booted. Of recently, we had a national microprocessor challenge in which Shakti played an important role. There were more than 5,000 plus teams which basically participated in this effort, and many applications were ported onto this particular platform. So the bare metal is something very important for application development, and we have enough resources to do bare metal embedded programming on the Shakti environment. In addition, we have also ported the Linux kernel 5.5. We have completed the validation of the Ethernet and SD card drivers for that, and we are currently working on an HDMI driver and a single board computer Linux on FPGA, and we are also having an advanced floating point unit support for this. So these are the Linux kernel 5.5 related activity. On the security, we have completed the hypervisor extension. The hypervisor was freezed. The hypervisor specification was freezed by the International RISC-V Consortium very shortly, and in the just recent past, and we have now have a core which is fully compliant with this hypervisor extension, and we have certain secure software that we have booted on this, and I will explain you in few minutes about that. On the operating system part, we have the complete Linux kernel booted, multiple versions of this Linux kernels booted, like Ubuntu, Fedora, etc., and FreeRTOS, Zephyr, etc., booted onto this. And yes, as of this, we are planning to release multiple versions of Ubuntu and Fedora by December 2022. We also have language compilers that are booted, right? So C, C++, Java, OCaml, etc., plus GCC, CLang compilers, which are actually now executing. So you need not do something called cross-compiling. The compiler itself will be executing on a RISC-V machine, generating code, assembly code, or machine code for RISC-V. So these are some of the very important software efforts which we have taken, and we believe that these efforts are extremely crucial to bring up an ecosystem in the RISC-V. Another important thing is the courseware. So today, assembly language programming, one of the big success of the other contemporary processors were making this processor and its specification, and especially the assembly language, accessible to the students. And accessible, I mean that they should be given in a way by which they could understand, implement, and further appreciate the benefits of this instruction set architecture. So we have come out with a very unique lab for our undergraduate program. We tried it in the 4th semester of our computer science curriculum, in which these are some. I just wanted to share a set of exercises. So there'll be an exercise where people will, the students will write a C code and hand translate it to RISC-V assembly. For example, they do the bubble sort, or they do recursive binary search. They will write the C program, have a working program, and then they will translate it by hand into the assembly instruction. By this, they start appreciating how certain RISC-V ISA instructions can be used to realize the functionality of different constructs of the programming language. The next one is the mode switching. The RISC-V actually works in 4 modes: the machine mode, the hypervisor mode, the supervisor mode, and the user mode. These modes do exist even in the contemporary x86 architecture like the Intel and AMD. And why do we need 4 modes? We need 4 modes because the operating system has 4 layers of execution, and so you can match the respective layers onto the respective modes. Each of those layers in the operating system has certain privilege levels. Similarly, these modes also have certain privilege level. For example, the machine mode is the highest. Its number is 3, and it is the highest privilege. That means all instructions, all memory can be accessible through the machine mode. But then when we go on to the hypervisor mode, there are certain instructions that cannot be executed in the hypervisor mode, and certain parts of memory can be isolated from the hypervisor mode. So like that, as you keep going from the machine mode to hypervisor to supervisor to user, the strength or the power of these modes decrease. The power is measured in terms of the number of type of instructions they can execute, and also the memory that they can access. So this gives a perfect platform for building an operating system with necessary inter and intra-process security, and that is something that we teach as part of the exercise number 2. Exercise number 3 is extremely crucial, wherein we teach the students about exception handling. Right? How do you set up interrupt tables? How do you, when an exception comes, how does an exception handler take control? So these things are basically the students write assembly code to understand exception handling. The fourth, which is very important for modern operating system, is the virtual memory. And the RISC-V today supports multi-level paging, and so we have an exclusive dedicated assignment in which, using an assembly language, they set up the page tables, they do access, and they simulate, or they actually land up with a page fault, they recover from the page fault. So they understand, the students essentially understand all the page table setup, etc. And then we also look at what we call as physical memory protection. The PMP in RISC-V is something equivalent to segmentation from the privilege level perspective of the x86 architecture. The x86 architecture, followed by Intel and AMD, has segmentation, by which each memory can be, when a program executes, there can be dedicated code segment, data segment, stack segment, etc. Similarly, here we have something called physical memory protection. So when a process is executing, you could have several physical memory layers, and each of these layers could have access privileges, and they can have privilege levels. For example, each of these one memory can be designated that it can be accessed only by the system and not by the process. So there are many things that you can map onto this and ensure inter and intra-process security. And so we also teach PMP as a part of this courseware. And the last one is XV6. This was actually promoted by MIT, where XV6, we have this is a abridged Linux, a very small Linux, around 8,000 code, and on which people can do multiple assignments, and they can write their own schedulers, they can write their own memory management units, they can write their own interrupt handling routines, they can write their own system calls. By this course, so the XV6 was currently done using the x86 or the Intel processor. Now it has actually moved on to now the RISC-V. And so we teach an operating system course based on the RISC-V architecture. And this is also something very important. So the students do the assembly programming course, the 5 assignments that I put on the right-hand side top, at the end of their 4th semester of their undergraduate program. And in the 5th semester, they do this operating system course. And all this put together will make the student quite comfortable with the RISC-V ISA, not only understanding the basic arithmetic and logical instructions, but also the most important part of the microarchitecture, which serves certain system-related functionality, the operating system-related functionality, inter-process protections, and the very advanced topic like virtual memory. So this is something that we have done for the academic world to bring in RISC-V in its full form. On the SDK, we have several software development kits. So you can build and run applications on top of that. We have the Shakti SDK, and we also have an integrated development environment which can be used for rapid prototyping and application development. And this is also indoor developed. All these are available free. We also host a set of sample applications, and the examples are also there. So people can download these examples, burn them on to an FPGA and do that. And then there are some start learning the basics with our study guide. So this is also available. And we also have a very important blog where we write many things about the Shakti processor, so that people can quickly get onboarded onto using the Shakti. We have a lot of video manuals. We have programming Shakti onto the FPGA. We have part 1, part 2. There is a Shakti SDK installation. There is a video, and how to add a simple application to Shakti SDK. So all these things are already part of this. And all these manuals and the software development kits are available for free at shakti.org.in. the thing that you see, the website that you see on the left bottom of the screen today. Now, the other very interesting thing that we had done was the for promoting RISC-V in our country was this Swadeshi Microprocessor Challenge. Swadeshi stands for indigenous, so indigenous microprocessor challenge. We had several 32, 64-bit RISC-V variants from CDAC and IIT Madras. So the CDAC processor is called the Vega processor, and IIT Madras is of course the Shakti processor. We had around 5,000 plus registration teams. So around each team has an average of 2 to 3. So we are looking at between 10,000 to 15,000 participants, out of which 100 semi-finalists were shortlisted, from which 30 finalists were taken, and top 10 winners are supported by MIT to promote RISC-V based products. And this, we got it as a part of this entire effort. So these are the this is another very important milestone. This was recently concluded last but 1 month in November. The challenge was completed and the winners were announced. Now, I would like to spend a few minutes on this topic of what we call as the separation kernel. Today, separation kernel is a very important layer that separates the hardware from the operating system. Why do we need such things? Because when countries buy microprocessor, buy third-party software, both the microprocessor is really a black box, and then the software is also a black box. So when you take executable, it's highly impossible for us to find out the trust of those things. So how do we try and manage this? So for any malicious attack, if at all it's going to be done, it should be a coordination between the hardware and software, right? So between the operating system and the hardware. Now a separation kernel is one that stays in between this hardware and software, and it will monitor the execution of different software modules on the hardware. And if there are some malicious type of execution, or finally a malicious code should execute on a processor to manifest its maliciousness, right? And so this particular kernel that sits between the hardware and the higher layers will find out if there are certain issues and can report. So separation kernel becomes extremely important. And on top of this separation kernel, you can have these multiple operating systems built as virtual machines, and each machine can be put into a container. So the picture that you see on the left hand side has a Shakti hardware core, and it has Triumph, which is the separation kernel, in the middle, and then you could have multiple operating systems on top which can basically execute on this hardware. And the separation kernel can basically monitor all these execution of an operating system on the hardware, and if there are certain issues, it can trigger them. It can warn the user about it. So now this. So as we saw, this is one thing very important. So the Shakti hardware has a microarchitecture. Then it has a middle layer, which is the hypervisor. So there's a machine mode, then a hypervisor mode, then a supervisor mode, and the user mode. The operating system, as you see on the top of the figure in the left hand side, can work on the supervisor and user mode, while the machine can execute certain boot code, etc. in machine mode. The hypervisor mode can be used exclusively for this separation kernel, and this is the idea by which this 4-layered operating system and correspondingly 4 modes of execution has come up. Now, so we had finished this full-fledged RISC-V hypervisor implementation. Triambak is the operating system from a startup company in Bangalore. Bangalore is another the Silicon Valley, the Bay Area of US. We call it the Silicon Valley of India, where we have many startups and majors, MNCs who have set up their shops for doing semiconductor electronics and system design. And so SecureWeave is a startup company based out of that Bangalore, and so they have developed this indigenous separation kernel. We have ported this onto the Shakti platform, and it works in the hypervisor mode. So exploiting the hypervisor mode of Shakti is a very important thing, because that gives the ultimate security. Once you have such a separation kernel, then it will be extremely difficult to launch certain attacks, including the rootkit attacks, etc. Now, in addition, the Shakti security artifact supports what we call as high assurance boot, wherein we have certain one-time fused keys using which things are encrypted, and on boot the code is decrypted to find out if there is any change made by anybody to that code. So if there is some change, that means there is some malicious attack that is part of this, and then one knows how to handle those attacks. So these are very interesting, very important part of our operating part of our secure Shakti development. Now, with respect to the RISC-V and IIT Madras, RISC-V has many teams across, and what we have today is the IIT Madras makes a lot of participation on the vector, on the base ISA opcode, etc., and also on the debug and also memory module. So we participate very much in the various RISC-V foundation related activities, and that gives us a good interaction. Not only that we understand the RISC-V, but we also have a good connect with all the major industries across the world who have who are very big stakeholders in this entire exercise. As you see on the screen, we cannot name a big company whose logo is not there in the screen. So all the companies, we have AMD, we have Intel, we have Western Digital, we have Sci-Fi, we have BAE, we have Nvidia, Micron, Google, whatnot. So these are all the people who are part of this entire exercise, right? So IIT Madras is also very much into what we call as the RISC-V architectural compatibility. Suppose somebody comes out with a architecture, say somebody comes out with a micro architecture saying they have implemented RISC-V. How do they now go and find whether they have really implemented all the functionalities of RISC-V? So we make certain assembly tests which will help them to run. You run it, and then the success of those tests essentially implies that they are compatible with that aspect of the RISC-V architecture. So we have been actively working with the RISC-V Foundation on getting these compatibility tests. So the complete framework for compatibility test is currently available. We call it RISC-OF. This is a RISC-V compliance framework. This has been authored by IIT Madras, and through this we can define cover points, we can automatic generation of assembly instructions and coverage reports. We can generate these. So RISC-OF is actually available for download through the RISC-V Foundation websites. And we have also done, in addition to the the framework, we have generated compatibility tests for single precision and double precision floating point, which is IEEE 754 compliant. We also finished off, now we have finished. Sorry, I didn't update the slide. We have finished the crypto scalar and bit manipulation RISC-V extension compatibility tests. And currently we are working on half precision float and floating point in integer registers, the Z Finex, right? This is floating point in integer registers, and those compatibility tests will be available by Jan 2022. Now, coming to the last part of my talk, I'll be finishing in next 5 minutes. Coming to the last part of my talk, we had this is the Shakti roadmap. This is basically driven by what we call as the distributed AI ML based cyber physical systems that are currently part of our the world, transforming or defining the digital transformation of the world today. So when we look at these type of large scale systems, we find 3 or 4 type of SOCs that are necessary. The 4 types of SOCs include the D1, which is a micro edge device, basically used for typical applications like pollution sensing or water flow sensing, some environmental monitoring. The D2 is medium edge devices, which can be used for industry 4.0, process control, vehicle electronics, etc. The D3 can be used for network routers, mobile phones, desktops, workstation, while the D4 is for decision making and monitoring, which can be used for cloud, transaction processing, supercomputing, etc. So as a roadmap, we are envisaging 4 normative architectures or SOCs. The D1, which will be a deep embedded extreme low power with optional low power radio and NAVIC. NAVIC is the Indian GPS. And we have this edge and deep embedded devices which can use these SOCs. And this should be specialized ultra low power variants that can be used to designed to use power harvesting. The D2 is a standard embedded SOC with 1 to 8 in-order cores that we are talking of the C-class cores and capable of running autos and MMU-based OS like Linux or Secure L4. The D3 will be the mobile desktop grade SOCs with 1 to 8 in-order / out-of-order cores with vector processing units and optional AIML accelerators and GPUs, and this can be used for secure mobile desktops and high-power embedded applications and low-end servers. The D4, which is a secure server SOC, with the 2 to 32 number of out-of-order cores with VPUs and optional AIML accelerators. So these are the 4 normative SOCs, which the derivatives of this can be used on multiple domains and essentially take it forward. So this 4 SOCs can define the entire computing need of a digital world. So with this, this is our roadmap, and with this, I thank the organizers for providing this excellent opportunity to interact in this RISC-V day. I look forward to multiple collaborations between the different participants today, along with IIT Madras. And with this, I open up for questions. Thank you very much.
Thank you very much. Thank you very much. Can you hear me okay?
Yes, I can hear you.
All right. So thank you very much for interesting presentation. So I have like maybe a couple of questions, because I remember like in maybe as early as 2014-15, IIT was very aggressively starting to be part of the RISC-V effort. Can you actually give us some background on how that happened?
Okay, thank you very much. This is a very exciting question. In 2012, we were inspired by our former president, Dr. Abdul Kalam. All of you might know him. He has been an inspiration for several youngsters at that point, including many of us in our department at IIT, where he said by 2020, all of you should do something that is very concrete for the country. At that point, we being computer architects, we thought, why not we do a processor of commercial grade and release it in 2020. So 2012, we started this effort for bringing up a commercial grade processor by 2020. At that point of time, we started with the open power architecture because we wanted to have an open source architecture. So we started with the open power. Power in Sanskrit is Shakti, and that's how the name Shakti came. And when we started looking at it, the overall learning that we need to do was quite phenomenal. To bring out a complete indigenous design, changing things across, uh, there was a lot of development that had been already done, and we found it could not meet our deadline. At that point, Nikhil from BlueSpec actually visited us, and he said that Berkeley is already into developing its own instruction set architecture. They are at a very advanced stage, and he himself has coded some of that because we were using BlueSpec, and he also said that BlueSpec is very actively working on it. And he said, why don't you start looking at that? And when we looked at the RISC-V ISA, we realized that it is going to be open source, and importantly, for the benefit of all the people who are attending this, the RISC-V ISA is released under the BSD license. Essentially means you can change it and you need not report back what you have changed it. So it's a completely encumbrance-free ISA given to you. So that actually suited us very much. And then this open source ISA, and then there was a major sort of, at that point, at least 4 or 5 of us got into it, including MIT, Berkeley. IIT Madras was one of the early founding members of this. We joined with them. And then we had Cambridge, some efforts going on, and somewhere in Europe also started. And then we decided, one night decision, July 23, 2013, we decided that we now move on to RISC-V. And from that, we did not look back, and the journey has continued. Thank you.
Okay. So I have an agreement with the succeeding presenters, so we can delay a little bit. And I have another question. You showed at the Courseware that I think parallels very well with that ACM curriculum back in the way, over there in the States. So are these like a Courseware? Actually, how did you come up with all these curriculum?
Very nice question. Very interesting question. So today, when we started building our chips, we wanted people who can hack the kernel, right? This is an entirely new architecture, and we wanted people who can understand compilers, who can understand the kernel and understand the entire boot process, etc. And for actually understanding the kernel, we need to understand lot of the microarchitecture, not just the so assembly language programming on the whole essentially means only the arithmetic and logical instructions, but that were not sufficient. The many part of the operating system still, even if you look at Linux for the x86, many part of the operating system are still written in assembly, right? The initial parts before the actual kernel boots. Now, and that assembly actually has interrupt service routines, has things that can enable virtual memory, has certain memory management unit functionalities, has some mode switching, etc. So all that we have put on the exercise were culminating out of this type of an understanding that somebody wants to port a kernel, an operating system, onto the new architecture. What is it that they need to understand about the microarchitecture from the system functionality perspective, like the interrupt service routine, etc., etc., and how do you relate this with actual booting of a kernel, right? So the XV6 education along with this, this assembly language programming education, both merged together essentially became a killer for us. Killer in the sense it was a jackpot for us. So as you know, the necessity is the mother of any invention. This necessity to have Linux kernel experts was the one that drove us to come out with this type of courseware.
Okay. So
Thank
we
you.
still have like 3 minutes. One more question. That is, bare metal, like where that you make the students design, like SPI UART, I2C UART, GPIO PWM.
Yes.
I think this is very strong program, but what is the background? I mean, how did your colleagues and you just actually chose to kind of implement this type of stuff in
Yeah.
addition to all these other things?
Yes. Yes. So again, that was also a necessity because when we started this program, as you know, we when we wanted to make those chips, we were not having much fund. And if we wanted to buy these peripheral IPs from commercial vendors, the cost was prohibitively large for a design which we are yet to prove, right? So when we made our first chip, we did not know whether RISC-V made by IIT Madras will work or not. At that point, when we wanted to build an SoC with multiple peripherals, etc., I think we did not have the funding to buy commercial grade IPs from IP vendors, and it was prohibitively large. It was almost $250,000 for just purchase of those IPs, and then there was a lot of integration efforts at that point. But when we want to make the chip, we cannot make the SoC without peripherals, because then we will not know how to validate it, right? So we wanted to interface with multiple peripherals and multiple sensors and write some programs and validate many of these things. So that drove us. So we had multiple student projects. We started off with student project. Today it has come out very well. 3 chips and all these are working. Essentially means that the designs are stable, wherein we gave these as the project definition, and we got this I2C, PWMs, UR, DMA, MMU, all these things done as projects, and then we validated. We now have our own verification IPs, and we validate that, and then put it onto the chip, and ultimately it worked. So this is the actual, again, the necessity drove us to make such indigenous IPs, and we continue to make. So we are doing an I2S now, because if you want to get these IPs from a commercial market, that's going to be extremely costly.
Incredible. Thank you very much.
Thank you. Thank you very much.
So I think I need to thank you very much for your presentation and contribution. And then I would like to just actually move on to that next presenter. Thank you very much, Professor Kamakoti.
Thank you very much, and thanks for this opportunity. And I invite all the attendees to start for a collaboration with IIT Madras. We are always open. Our sources are open core, and our intentions are also open. So I take this opportunity to invite all of you to the Shakti program. Thank you very, very much.
Thank you.